welcome to day 14 of the 30-day coding challenge here from CSandMath. We were talking about Spiral of Theodorus, which is a great exercise in geometry. We're on day 2, and we're finally going to bring in these two pieces today, Pythagorean Theorem and Trigonometry, through the math package. So let's jump right into it. So I've gone ahead and pasted the code right into our trinket, and this is, if you missed day 1, code that's short enough that you could copy it right now. If you weren't sure what it does, then go back and watch that video from day 13. But if I play this and it moves fairly slow, I can see that it draws the first stage of our spiral. If you missed that, we're talking about this classic spiraling of a base 45-45 half square, right triangle, and basically building off that. Now what happens in each succession is that the new triangle, the next triangle, the first leg, which is like this short leg, actually travels the hypotenuse of the previous right triangle. So this first move in the second right triangle is going to be the hypotenuse of the first, which is where the Pythagorean theorem will first come in. So let's jump to that. So if I was in here, notice the way we have it is we say we travel forward A. Just to remember these lengths. This is a little sloppy too. Let's set up some hashtags in here. And this is just commenting, remember, so this is going to be my setup. And then after that, this stuff right here is what is going to build the spiral. Just so I can kind of have structure to my code. And now if I just focus on the stuff that's building the spiral. So I set this length to 1. That was to have something we could easily increment up when we're talking about the square root path that we're traveling. So again, if we look at this, the pattern that kids will notice when they calculate the first few, if they were doing this by hand, was that, okay, this hypotenuse is root 2, this hypotenuse is root 3, and root 4, and root 5, and that's the classic pattern that we want them to see here. So we just want to be able to increment that calculation up through each repetition, which is why we created a variable there called length. You could call that anything, not just length. So A, we called this first leg movement here, this first forward movement, we called that A, so that's why it says forward A. I'm going to also take this speed out of here. Again, this is just part of writing fairly clean code, so people that were coming in here could easily follow it. Even you could separate the declarations of the variables here, and then the moving would be nice. So then we turn 90 at the corner. We move forward B, which we set to be 50. Remember, 50 pixels. Space that out to make it look clean. And we could set that to something else. Let's say like 100 or something like that, right? It's worth noting that the places that we have 50, so B is equal to 50, we should probably just put a B here then, right? Because that's that B length, which is like our base scale length. Whatever this outside value is, remember, stays constant, like 1 and 1 and 1 and 1. That is one of our constant values we said yesterday. So that is going to be replaced by a B, and then I'd replace this one also with a B. And this was the structure we left off yesterday with. It's worth noting that if we tried to run this right here, it would produce an error, right? Because definition of A actually uses B. So in terms of declaration, we probably should say, okay, well, we got to define B before we use it here, right? And then we get this base triangle set up. Okay, then the first thing we're going to modify, and I would really have you do the same with kids, is if we look at this, we're traveling A, we're traveling B, but when we travel this one, and what I have in line 17, forward dot B times the square root of 2, well, that's only going to work in this base triangle, right? You can go whatever this B value is and multiply that by square root of 2, and it's going to give you this length. But this one's not like that. This is times square root of 3 times square root of 4, and so on. And so there's a couple ways you can put that formula in. I would just tell them that this is your classic Pythagorean theorem, right? A squared plus B squared equals C squared. So the C squared part, right, you'd have to square root. So I guess we'd still start off with math dot because remember we got to get this function from the math package. Square root doesn't just come pre-standard. So I'd type square root of a to square. You can put 2 asterisks, so instead of multiplying with a single, so that means a squared plus b squared, parenthesis. Now notice if I have that single parenthesis there, that's just closing off this one. It lightly highlights it there, but to close off this original parenthesis, we need another one there. And if we run this, notice that now we've traveled the hypotenuse, which is what we're going to consistently do every time we update what the a value and the b value are. So that's the easier of the two. We've just incorporated Pythagorean theorem that we're going to do over and over and over, and in the program we'll recalculate it once we start looping through and drawing multiple triangles. The second piece is to put in something other than this 135, right? Because that angle right here is 45 degrees, right? We said, which makes this exterior angle, because we were traveling up this way, this exterior angle coming off of what would be straight vertical was 180 minus that. And this will definitely be a hard step. It's kind of tricky, but we think it's valuable. So maybe to give kids a good fresh start on this, delete out the 135. And again, there's ways to avoid this, but the math and the questions that come up with it, we think are really valuable. So if I go to this image I have up, you could be like, well, let's just look at a right triangle that we've looked at a lot. Hopefully you've looked at this with them. If not, just say one of the most basic common right triangles is a 3, 4, 5 triangle that we'll look at a lot, right, where a squared plus b squared does equal c squared. You'd think that this angle that you'd be turning, let's say if it was that, was a nice easy angle, like the 45 angle that we did in the half square, right? But it turns out that it's not. It's an ugly angle, and the way that you find it is with ratios. And you don't have to worry about stealing this if you're doing it before geometry. You're just introducing them to a concept and showing them, maybe even getting excited to anticipate it later on. So if I did this progression with kids early before geometry, I'd just say like, yeah, one way we get this ratio is to capture all of them. Like we go opposite from that angle. We say, well, we have a length of 4. So we say like, well, the ratios are actually stored up. They're always the same for this type of triangle. And this leg right over here is adjacent to that, right? And you can talk about that as much as you want and don't feel bad about it. And so then you'd say, well, this ratio using the 2 legs, almost like a rise and a run, like slope, is called tangent. And we actually get the tangent. There's buttons on your calculator, excuse me, where you could do the tan inverse. I don't know how much of that you would want to show them, but equals that ratio. So for now, just showing them that basic structure would be valuable. Okay, so then I've jumped onto Desmos, and I would tell kids like, okay, well, that angle, if we use this concept, and you'd have to, whatever technology is showing them that you're comfortable showing. I could print it too on Python, but that angle is an ugly one. Like it's not just 53, it's 53.130, yada yada yada, right? It's all this stuff to get it drawn accurately with precision. And not only that, we don't want the interior angle. We want 180 minus that. We want to determine this exterior angle, which is, something you can calculate as well. And then you should talk about, I already went into Desmos, and Desmos actually defaults to radians, so they might get confused by that. And be like, yeah, there's actually more than one way to measure angles. It's not just degrees. And later on, when you get to upper level math, you'll talk a lot about radians and how they're actually sometimes more useful than degrees. Just like sometimes you measure in centimeters and sometimes you measure in feet, right? They're different, but both have their places. So in Python, you could find in the math package that that angle that we're going to turn is math.atan, like arctangent, because this angle right here, right, has this ratio of a over b. So the arctan of a divided by b. Close that one, close the previous one. So that should close both. And now if we did this, I'm going to turn these two off and run this. Notice that when we say to turn left, it doesn't even look like it's really turned. That's because, like Desmos, Python defaults to radians. So we have to say math.degrees and convert this measurement to degrees. Which I know again is ugly, but now if I run this, notice how it did turn. And then hopefully you'd say, oh, wait a minute, that's pointing in the wrong direction, right? That's because this is the interior degrees, and we have to take 180 minus that. And now if I run this, we get what we want. So I know that that's tricky, and you might say, well, it's too much to do with kids. You can give them that line and say you'll talk about trig later. We're just trying to say there's value in talking through that structure. So now you have it right here. We have included both the Pythagorean theorem in this line and trigonometry in this line. Okay, I previewed some code there. I'm just trying to think of a nice way to clean this off for today. And what I think we should do is just try to do a for loop so we can loop this code twice. So right above here, put that for item in range 2, which we've done in previous videos. We're going to tab that all into the loop. Remember that this length that we're doing, like this square root of 2 length, we have to increment that each time. So length for the second triangle isn't going to equal the square root of 2, it's going to equal the square root of 3. So we need to increment that length up one every time. And we're going to have to reset the first leg length, right? Because in the second triangle, if you see I've already ran that, that needs to travel the new A length, right? Because the new A is going to be equal to the recalculation here. So I'm going to take this chunk out, cut that, and put it in the loop. And notice if we run this, it makes the first triangle and makes the second. And you could play around, run as many loops as you want, and we will finish this spiral off tomorrow. Thank you guys for watching.